liars and murderers have their part in the lake of fire and brimstone.
Brimstone is in Group 16 under oxygen. Sorry, I mean sulfur. Group 16, the chalcogens, another p-block element with atomic number 16. When heated to about 120 degrees Celsius, the familiar yellow solid melts into what we call S8 rings. Small crown-shaped molecules of sulfur. By 160 degrees Celsius, these rings break open and link together, forming long polymer chains, and the liquid thickens into a dark red syrupy mass. As the temperature approaches 200 degrees, the average length of these chains begins to shorten, because the balance between making and breaking sulfur-sulfur bonds now favors breaking. The liquid becomes runny again, but stays a deep red. Finally, at 444 degrees Celsius, the boiling point of sulfur at atmospheric pressure, after turning almost black, it evaporates. On its own, its vapor would be invisible, but when it reacts with oxygen, it glows with a beautiful, vivid blue flame. This is the emission spectrum of diatomic sulfur and sulfur dioxide. This sort of color is rare among the non-metallic elements. This is the sulfate ion, sulfur with 4 oxygens, 2 of which are negatively charged. The sulfate ion has 32 valence electrons. The sulfate radical, however, has 1 less electron, making it extra reactive. Most radicals are reactive, but the sulfate radical takes it to another level. With an oxidation potential of over 2.5 volts, it's a molecular wrecking ball. The moment it forms, it rips electrons off almost anything it touches, breaking down molecules that other oxidants won't even scratch. Sulfuric acid is not just an acid, but it's an oxidizer and a dehydrator. The famous carbon snake experiment is an example of sulfuric acid as a dehydrator. It rips water molecules from the sucrose, leaving behind amorphous carbon mixed with residual acid, char, polymerized organics. The snake is expanded because of steam and sulfur dioxide and sulfur trioxide gases pushing through the carbonaceous foam. Concentrated sulfuric acid, preferably 98%. We are going to drip this onto phosphorus pentoxide. This is how phosphorus pentoxide reacts when it touches water. This is now warm. Phosphorus pentoxide, as I mentioned in my video about phosphorus, is considered one of the most powerful desiccants known. It doesn't just absorb water, it chemically binds it, forming phosphoric acid. One drawback, however, is that phosphorus pentoxide cannot easily be regenerated once it has reacted. That's why more practical desiccants for routine use include magnesium sulfate, calcium chloride, or molecular sieves. They are weaker but can be reused. Another strong and chemically reactive desiccant is sodium metal, which is used for drying ethers and hydrocarbons. Close in strength to phosphorus pentoxide is calcium hydride. This reacts with water to release hydrogen gas, making it another aggressive but useful drying agent. If we want something even stronger than phosphorus pentoxide, that would be sulfur trioxide, the compound we're making today. For sheer dehydrating strength, only sulfur trioxide surpasses phosphorus pentoxide, but it's far less convenient to handle. These substances are at the extreme end of the scale. They don't just dry samples, they can destroy them outright, and their destructive power is something you always need to consider. The short path condenser, positioned like this. I'm going to measure the temperature of the condenser water because we need it to be a bit warmer than this. 25 is good. I will now open the stopcock so that the sulfuric acid will drip on the phosphorus pentoxide, where it will release sulfur trioxide vapors, which will condense in our 25-degree condenser and collect in the test tube. Sulfur trioxide fumes in air and it reacts strongly with water. Drip. Drip. Very tiny bit on the end of a spike. The sulfur trioxide made here is dissolved in
little smoke ring.
concentrated sulfuric acid.
It will dissolve.
This results in a more than 100% sulfuric acid. This is called oleum.